Hello viewers, in the first part of my lecture on catalysis, I introduced you to the subject, and in today's lecture, let me recapitulate what exactly was done in the first lecture. Importance of catalysis in industries that I told you, why it is important, what catalysis means and what is a catalyst, the definition. A catalyst is an auxiliary substance that is added to the reaction system which increases the rate of a reaction. Classification of catalysis into homogeneous catalysis and heterogeneous catalysis, and also a special category, enzyme catalysis, the nature's catalysts. I gave you some examples of catalyzed reactions and the characteristics of catalyzed reactions we looked at. Finally, I told you about one of the theories, which is the intermediate compound theory, which mainly tries to explain how homogeneous catalysts work. Today, I will discuss about adsorption theory. To know adsorption theory, we must also get an idea about physical adsorption and chemisorption. And once we do that, we can try to explain the heterogeneous catalysis in terms of what is called a 5-step mechanism. Since the catalysis takes place on the surface of the catalyst, we must look at the surface. What exactly must be happening there? How a surface is able to catalyze the reaction? Active centers that are present on the surface. And then how catalyst poisons work, which destroy the activity of the catalyst. Let us start with adsorption theory. This is applicable to heterogeneous catalysis because adsorption is a surface phenomenon. We generally use solids as catalysts. Adsorption of the reactant at the surface of the catalyst is a must. That is the basis of this theory. Now, the question arises, is it physical adsorption or chemisorption that we are talking about? Let us look at the difference and their roles. The surface of a solid has a tendency to attract and retain molecules from its surroundings with which it comes into contact, and this phenomenon is called adsorption. This is what you have studied in physical chemistry elsewhere. But then, if the adsorption is by van der Waals forces, that the molecules are retained on the surface by van der Waals forces, then it is called physical adsorption. And if the chemical forces are involved, where the molecules are held very strongly by means of chemical forces, then it is termed chemisorption. Now, what is relevant in the case of catalysis? This figure will help you to understand the phenomenon. Here you have the surface and a molecule approaches the surface. As it comes closer to the surface, it experiences attractive force, the energy therefore decreases and it has come to an equilibrium position where it is held by weak van der Waals forces. This is the potential energy well. If it tries to go closer, the energy increases. On the other hand, if the molecule approaches, say in the dissociated state, hydrogen molecule has dissociated hydrogen atoms, and then as it approaches, the stronger forces, chemical forces act on it and the energy decreases substantially. It is a deeper well than what you have seen here. It is chemisorption, to be brief, and then you can see the molecule has gone very close to the surface and further if you try to force it together, the energy increases drastically. Now, this will tell us the heat of adsorption in the case of physisorption is less, whereas heat of adsorption is large. And in this value of heat of adsorption is very close to the bond energies, and therefore, it appears that in the case of catalysis, chemisorption plays its role. Then what is the role of physical adsorption? The physical adsorption energy changes involved is not much enough to distort the molecule. Therefore, the role of physisorption is to get the molecule close to the surface. Once it has come close to the surface, slowly that molecule can pass on to the chemisorbed state. And the point of intersection you can see here, it is on the plus side, and therefore, this type of adsorption is called activated chemisorption. And if the point of intersection is below 0 here on the negative side, the physisorbed molecule can easily go to the chemisorbed state. Then it is called non-activated chemisorption. And in such cases, we can call the physisorbed molecule to be in the precursor state. That is how we can find the use for physisorption, bring the molecule closer to the surface, then the molecule gets chemisorbed, and a chemisorbed molecule is actually prepared for the reaction, as we shall see in slide here. Now, you have nickel surface, a hydrogen molecule has approached, and you can see the dotted line which gives us the van der Waals radii. The molecule is far apart, but still held to the nickel surface, but not strongly enough. But here the nickel has been able to break the bond between hydrogens, and hydrogen is now adsorbed in the form of atoms, and this type of adsorption is called dissociative chemisorption. Now, you have prepared hydrogen molecule for the reaction already. That is why nickel is a very good catalyst for hydrogenation and dehydrogenation reactions. We can draw an analogy here, and suppose the nickel surface is the teacher and you are the student, you are in the last bench. So, you are not held strongly, you can escape from the class when the teacher is not looking your side. But if you occupy the first benches, it is very difficult for you to escape teacher's attention. Therefore, a chemisorbed molecule is held very strongly, and therefore, it is able to contribute towards the reaction. Now, look at how strongly the molecules are to be held. If the strength of chemisorption is weak as measured by the heat of adsorption, the concentration of the molecules on the surface will be less. So, the rate of reaction in terms of activity will not be high. But if the strength of adsorption is too high, then again we have problems. The molecules will not leave the surface, they will act as catalyst poisons. Therefore, the strength of adsorption should be somewhere in between, that is the optimum strength, which will be favorable for our catalytic reaction. Now, look at some activation energies for heterogeneously catalyzed reactions. If you can look at the value here for the reaction in which hydrogen iodide decomposes to give you H2 and I2, uncatalyzed reaction has an activation energy 184, and when compared to that, the catalyzed reaction first on gold surface and then on platinum surface, it is 105 and 59. You can clearly see that these are the surfaces on which the reactants have tendency to get adsorbed, and one is better than the other. The second example also is about the oxides of nitrogen, that you can see how nitrogen dioxide gets decomposed into nitrogen and oxygen on the surface of gold and platinum again, and you can see in this case you can see platinum is not as good as it was in the earlier case. It has not been able to bring down the activation energy to lower levels. Just for comparison, I have given you a homogeneously catalyzed reaction as well. This also brings down the activation energy. Now, look at what exactly must be happening. This is the surface of the catalyst. We have molecules in the gas phase, and according to kinetic theory, the molecules are moving at random, colliding with each other and colliding with the surface of the catalyst. Now, you have a favorable situation here. There are two types of molecules. The molecules have occupied the positions very close to each other and they can react, and that is what we are interested in. That is how we try to explain. So, this is explained in terms of what is called a 5-step mechanism. The first, molecules diffuse to the surface of the catalyst. Adsorption of the reactant molecules on the surface takes place. There is formation of an activated complex, a surface active complex, in which surface atoms participate and favor the reaction. Once the product is formed, the product must diffuse away from the surface. Before that, it has to get dissolved. And these sequence of events we can pictorially see here. You have the surface, the molecules of the gas phase are here, they are moving at random and they have to diffuse to the surface of the catalyst. And not only that, they must occupy positions very close to each other. They are called the sites on the surface, and in the second step you can see the molecules get adsorbed, the bonds are formed, and once they are together there is a tendency for them to interact with each other. Surface favors, surface has brought them closer together, they are occupying sites very close to each other, they are in a position now to form what is called the surface active complex. Surface is part of this complex, and as this complex is formed, the bonds with the surface become weaker, they are ultimately snapped, resulting in the formation of the product, that is AB, that we can see here. The product is formed. Once the product is formed, this product gets dislodged in the desorption step. Once it gets dissolved, the molecule of the product diffuses away from the surface. Now, surface is free, and the step number 1, 2, 3, 4, 5 starts again, the next cycle. The surface of the catalyst is ready for the next set of reactant molecules. That is why I recall the Chinese definition of catalyst, sue me, the marriage broker. This is exactly what is happening on the surface of the catalyst. Let us take an example of a reaction in which hydrogenation takes place. Now, you can see the two molecules have got adsorbed, and the hydrogen has a tendency to get adsorbed in the dissociative fashion. You have the hydrogen atom, it is occupying a site very close to the methylene group here, and it establishes a bond to give the methyl group, and then the other methylene group, which is now adjacent to a hydrogen atom, interacts with it to give the saturated ethane, which then diffuses away. The nickel surface is free to get other molecules so that the reaction continues. Heterogeneous catalysis. What a catalyst scientist looks for. He wants the catalyst to be having maximum activity. He has to work in that direction so that the production goes up, selectivity desired, but you can sacrifice to some extent, because if it is very highly active, then you can sacrifice to some extent on selectivity, and it must have stability, that means long life. The catalyst that is loaded must stay there in the reactor as long as possible. longer the stability, higher the stability, longer the life, more economical will be the process. If it is a short-lived catalyst, after every month you have to replace, then it is not a good economic proposition. You have to stop the reactor and reload a new catalyst. Now, you can look at some of the surfaces or catalysts that are used and the reactions that they can catalyze. You can see some relation here. There must be some chemical affinity between the surfaces and the type of reactions that they catalyze. For example, if you take alumina, alumina is a good dehydrating agent and therefore, it is a good surface for dehydration reaction. Choice of the catalyst. The catalyst must show detectable chemisorption. If it does not show, then it is not a good surface. Based on that, you have to have a short listing of candidates. Which are the surfaces that show chemisorption on the surface, not too strong, but show. But final selection will also depend on other factors, easy availability and the cost, because ultimately the industrial process must be economically viable process. Catalyst must have high surface area. Whatever material that you have selected on the basis of chemisorption, you have to get it in high surface area, and you have to add promoters also. Recall, what are promoters? Promoters are the substances that are added which increase the activity of the catalyst. Whatever is possible you add, somehow increase the activity, that is the target. And once you have got the catalytic material, in what size and shape? To increase the surface area, you can use powdered material, you can use colloidal material, but the best way that you have is to disperse the catalytic species on a support of high surface area. It gives stability, and most of the industrial catalysts belong to this class. And you can have the desired shape and size, granules, rings, spheroids and extrudates. You can compare different surfaces, all show chemisorption, all bring about a decrease in activation energy very close to each other, but one is better than the other. You can see in this particular case, rhodium surface is very good for the decomposition of formic acid. Surface of a catalyst is not uniform. Entire surface is not catalytically active. How do you get that? We call the surface is very smooth. This surface is smooth, I will say. But if you have a closer look at it, the surface is not smooth. You can see the ups and downs. Like if I use the probe, my finger as the probe, I will feel that it is very smooth. But if an ant walks over it, it feels ups and downs there. It will say that there are many potholes on this surface. And if you go further to the molecular level, the surface looks like this. You can see imperfections on the surface, and this is exactly what we want on the surface of the catalyst. And this idea came to H.S. Taylor. He said that on the surface of the catalyst, you have certain points which are catalytically active. You can see here steps, kinks, edges, add atom, holes, etc. And according to Taylor, these are the sites which are catalytically active. These are the places where residual forces are large. What is the proof? We need to look at what are these active centers and what is the proof that active centers are there. Look at the action of poisons. Poisons get preferentially and irreversibly get adsorbed on the surface, exactly on these sites. A small amount of poison is sufficient to destroy the activity of the catalyst. If the entire surface were uniform, then it should have poisoned the whole thing. but very small amount is there and it is not able to form a monolayer on the surface. Still the poison works effectively. Now, hydrogenation of ethene to ethane on copper catalyst is poisoned by a small amount of mercury. Mercury vapor can destroy the activity of the catalyst. Colloidal platinum is used for hydrogenation of ketones as well as aromatic nitro compounds. Now, carbon disulfide acts as a poison to this surface, but then the first reaction, hydrogenation of ketones, is totally inhibited, no activity, whereas the second reaction, that is aromatic nitro compounds, get hydrogenated, maybe with a reduced rate, still the catalyst works. Let me summarize what we have seen in this lecture. I recapitulated what we studied in the first part of the lecture. Then I discussed about the adsorption theory, and to understand adsorption theory, we must know what is physical adsorption and what is chemisorption and what is their role in catalyzing the reaction. Because these are surface phenomenon, the catalysis takes place on the surface of the catalyst and therefore adsorption plays a role. I repeat, if there is no adsorption, there is no catalysis. This has been beautifully explained on the basis of what is called a 5-step mechanism: diffusion of the reactant, adsorption of the reactant molecules, formation of surface active complex and reaction, desorption of the product, and then diffusion of the product molecule away from the surface. The surface is free to have the next cycle. A look at the surface. Surface is not uniform. Surface has some points or sites which are catalytically active. These are called active sites, and we have to try to have as many active sites as possible while preparing the catalyst. And then finally, how poisons act on the catalyst, and this helps us to understand what these active sites are. In my next lecture, I will discuss about enzyme catalysis. These are nature's catalysts. They are known for their activity and selectivity, remarkable activity and remarkable selectivity. Whatever discussion that we made about laboratory made catalysts that we use in industries, they are no match to enzyme catalysts. Enzymes activity is several orders of magnitude higher than the activity of any of the catalysts that we have prepared, and they are highly selective. Now, our aim is to prepare catalysts by imitating enzymes. Let us look at the details of enzyme catalysis in the next lecture, and in my next lecture I will also discuss about some of the examples, very good examples of catalysis in industry as well as maybe in our day-to-day life, where we come across a useful use of catalysts.